I've been here since about 1990. And most all of you know me. And it may be good or bad, I'm not sure. But we'll see how your opinions change after this talk. So I've given a rather engaging title, which I hope you won't mind. Oh, wait, how do I get rid of that banner at the top?
You can't.
You can't. Very good.
Sorry.
Okay. So unfortunately, the resolution on the screen isn't very good. But this is a picture of I believe it's M51, and there are two supernovae in, I think it's within a 5-year span. So whenever neutrino physicists live in that galaxy, they're very lucky. Maybe they got some extra funding because of that. I already know. Okay, so the kind of theme of this talk is that there's a very exciting time right now that I suspect is coming upon us quickly. So I'll ask this question: do we even know the fundamental physics that's necessary to understand the evolution of stars and compact objects? Clearly, we can understand a lot about stars with the physics we know. But as I'll show you, there are some things that are a little discomforting, and maybe some hints from observations, especially gravitational waves, but also from the laboratory, that maybe we don't know everything we need to understand, especially the evolution of massive stars and the kind of morphology of compact objects like neutron stars and black holes. So let me remind you of a bit of history. So in the 20th century, I claim there were broadly 3 real developments in understanding stellar interiors. One, of course, was just the advent of quantum mechanics. This was absolutely essential to answering Eddington's problem. You remember Eddington's problem might have been formulated as, gee, how come atoms can be ionized in a stellar interior even when the temperature is lower than the ionization potential? Of course, it was quantum mechanics to the rescue, what we would call in atomic physics continuum lowering, or the astronomers would call pressure ionization. So the key thing in quantum mechanics was really the connection between spin and statistics. That was absolutely key. And that allowed insight into what happens in stellar interiors. The second thing was the development of nuclear and particle physics. And there was a tight coupling between measurements made in the laboratory of nuclear reaction cross-sections and other things associated with particle physics, especially in the weak sector, in the beta decay sector. And that went hand in hand with astrophysical modeling. And I'll advertise that a key player in that development was the Kellogg Radiation Laboratory at Caltech that was headed by Charles Lauritsen and Willie Fowler, and that's kind of where I grew up, and also where Jeff and Margaret Burbidge were for a while. And then finally, of course, the other big development in the 20th century was the advent of large-scale computation that allowed stellar modeling. So here's where I think we are today. We have the standard model of particle physics, which is remarkably successful, except we know it's not adequate. It doesn't explain dark matter. It doesn't explain dark energy. It doesn't explain aspects of neutrino physics that we measure in the laboratory. So we know there's something more there. So here are some questions, for example. Are there secret interactions between the neutrinos and not between neutrinos and charged electrons? We don't know the answer to that question. Are there new light particles that figure in the physics of stars? We don't know that either. Are there new dark sectors of particles that are much like the standard model, perhaps, but different? The masses are different, the couplings are different. And circling back to dark matter, there are many ideas about dark sectors that purport to explain dark matter or aspects of it. Is dark matter self-interacting? And I'd say that the advent of multi-messenger astrophysics, especially gravitational wave astronomy, is already kind of a game changer here, and already giving really interesting hints about what's going on in answering these questions. So if I could just say, do we have this new regime that's arising, a synergistic coupling between the lab and observation? developing now that might have been a little bit like what happened in the 1950s and 60s and 70s. And it's exciting. There's a revolution in ideas about dark matter. We have a lot of experts on this here at UCSD. Tongyan Lin, a theorist, Dushan Karish in particle physics, Dushan Karish in modeling large-scale structure growth, Kaijuan Ni and Liang Yang in direct dark matter detection. There's a lot of activity in this area at UCSD. One thing I found very exciting was this program that we had this summer, dark matter and compact object stars and low energy experiments. This was at the Institute for Nuclear Theory in Seattle. And there's just this foment of ideas, new ideas about dark matter. The old days of your grandfather's dark matter of vanilla, non-interacting WIMPs that are utterly collisionless. Well, that may not be right. And instead, there might be many different kinds of dark matter with all kinds of interesting properties. So that's kind of where I'm coming from. So let me remind you about a few things, about very simple things about stars and self-gravitating systems. This also applies to some extent to star clusters. So sometimes they have negative heat capacity. So when an object like a star shrinks in its gravitational potential well, goes deeper in that gravitational potential well, it gives off energy leaks out, that drives it even deeper in the potential well, and it heats up in the interior. So when they cool off, they heat up. It sounds like Yogi Berra said that, like this: baseball is 90% mental, the other half is physical. Okay, he actually didn't say that, but I couldn't resist. Okay, here's the theme of this talk, another theme of it. These self-gravitating systems get into trouble when their pressure support arises from particles, I put particles in quotes, moving at or near the speed of light. So this could be a star cluster, for example, and for pressure, just read kind of velocity dispersion. So when the stars in a star cluster are all moving close to the speed of light, that star cluster will be unstable in general relativity. Okay. Likewise, for a star that's most of the pressure support is coming from radiation, from photons, or from electrons moving at the speed of light, like in a relativistically degenerate white dwarf, they will be unstable. So let me remind you about hydrostatic equilibrium, right? This is, we learned this at our mother's knee, and when we take stellar interiors. If I think about a fluid element in a star at some radius r, then I can add up all the pressure forces. Maybe I can, here we go. Add up all the pressure forces, just sum the pressure forces around the surface of that fluid element. And then figure out how much material is in that fluid element. And of course, its gravitation pulls it down. And I set those forces equal. So the forces balance, and I get the so-called equation of hydrostatic equilibrium. And here's what it looks like in spherical symmetry, right? There's a pressure gradient, and that balances gravitation, okay? What did I do here? All I did was equate forces. Oh, okay, but you have to be careful about this. So that's a mechanical equilibrium, the forces balance. That doesn't guarantee stability of that configuration, nor does it guarantee thermal stability. So, for example, stability against convection in a self-gravitating system would require that the entropy increase as you move out further from the center, okay? Nor does it guarantee chemical equilibrium. Okay, so not all the ions, the nuclear reactions, for example, have gone to chemical equilibrium. Okay, so how do we wrap our heads around this and look for stability? The key way to do that is the so-called adiabatic index. This was a terminology set down by Chandrasekhar. And so gamma 1, it is, and let me read it physically, it's d log pressure, d log density at constant entropy. So that means, so I can physically give you a picture of what the adiabatic index is. At constant entropy, just squeeze on material in the star, do it fast, so heat can't flow. That'll keep the entropy constant. So squeeze it to higher density and ask how much does it push back. Okay, that's what that derivative means. So it's effectively the spring constant of the material. Okay. So it's pretty easy to just do a simple perturbative calculation and find out that if in Newtonian gravitation, if we want to guarantee stability, the pressure averaged value of gamma 1 through the star has to be greater than or equal to 4/3. Okay. Now this is gamma 1 is much like the ratio of heat capacities that you might be familiar with from ordinary thermodynamics. Except Chandrasekhar, when he formulated this, was thinking of systems in stars where you had pressure support from non-relativistically moving Maxwell-Boltzmann particles in a gas and also radiation. Okay. So in such a gas, if we had no radiation, it was just particles moving slowly, then it would be pressure equals NKT, and pressure average value of gamma 1 would be 5/3. And if it were pure radiation, it would be 4/3. Okay. All right. Now, if we throw general relativity in the mix, even a tiny amount of general relativity, how is general relativity different from Newtonian gravitation? It's nonlinear. So a little bit more gravity makes even a little bit more gravity. So this is why, of course, this is what exactly the same as the physics that explains why there's perihelion precession of Mercury's orbit. Okay, because the potential is not quite 1/distance. It's 1/distance plus a little bit extra for that nonlinearity in gravitation. Okay, so what that means is for stability, if I put in general relativity now, for stability, that pressure average value of gamma 1 has got to be greater than 4/3 plus another term that's a very small term. That's something like, crudely, the Schwarzschild radius divided by wherever location you're at, the radius of the star. Okay, so that could be very small. That's like 1 part in 10,000 for a white dwarf, which is what we'll be talking about. Okay. All right. So again, I can think of this, consider a ball rolling on a surface as an analogy. So the pressure average value is gamma 1 is greater than 4/3. Then it's like a ball in a well. And clearly, if I perturb the ball from its equilibrium position, there are restoring forces that return it. However, if I have nothing but radiation pressure holding up the star against gravitation, and I have Newtonian gravitation only, then the pressure average value of gamma 1 is 4/3, and it's like a ball on a flat surface. It costs no energy to move that ball around, right? And likewise, if I had a Newtonian configuration with gamma 1 at 4/3, pure radiation, it would cost no energy to move the star inward or stretch it out. But now, when you turn on that first tiny nonlinear effect from general relativity, this criterion comes into play, and now there are no restoring forces. Now, when you take the star and squeeze it in, where you thought in Newtonian gravitation, you had radiation, and it was just neutrally buoyant, I could change it at any length scale. Now, if I move it in, there's a little more gravitation, so there's no restoring force. Okay. So this has a name. These two guys, the Feynman and Chandrasekhar instability, and you can read the foreword that Kip Thorne wrote in the write-up of the notes from apparently this guy's general relativity class from the 1960s. Correct me if I'm wrong, Lee, that points out that actually this was a problem on the final exam in Feynman's class. And of course, around the same time, Chandra actually did it also. But unlike Feynman, he actually wrote it up in a paper. Yeah. So, okay, so stars that are supported by particles moving at the speed of light are, and this is the words of my research mentor, Willie Fowler, trembling on the verge of instability. I love that phrase. Okay, so that's an opportunity. So small effects could shove these guys over the edge. That's intriguing. Okay. So in fact, if we look at this Feynman-Chandrasekhar instability, here are masses of various kinds of stars. And as you go up in stellar mass, think about it, you have to have more pressure to hold them up against gravitation. And there'll be the Maxwell-Boltzmann pressure of the baryons and the electrons, and that's going to go something like number density times temperature. But then there's the pressure from the radiation field, which is going up like 4 powers of temperature. So as you go up in mass, the temperature's got to get higher and higher, the density too, but that radiation is eventually going to win. So for very massive stars, they're effectively completely radiation dominated. So 10 to 100 solar masses, these are the sort of progenitors of ordinary fourth collapse supernovae, and we'll talk about those. 100 to 10 to the 4, and those get killed by the combination of the Enchanted cigar instability and various other kinds of weak interaction processes and nuclear processes. And in this range, this is where the electron-positron pair instability happens. So I'll mention that. And for the really big guys, 10,000 solar masses to of order 10 to 7 or 10 to 8 solar masses, these things never really have a main sequence. They're going down by the GR instability right away. Okay, so we'll talk a little bit about each of them.
Do you really think 10 to the 4, 10 to the 8 stars exist?
I don't care. And so I will tell you this. I'll use what Willie Fowler said and Fred Hoyle said. I don't care. But there are supermassive black holes at very high redshift. Where do they come from? What were their progenitors? Moreover, there may be dark sectors in particle physics that may aid in manufacturing things like this. Moreover, there may be star clusters, as Zeldovich pointed out in probably the mid-1960s or something, that could also suffer this GR instability and collapse. And in almost all cases, when those big star clusters start to go down, stars will be tidally disrupted and you'll get something like one of these stars. So it may be an intellectual exercise that has no basis in reality, but so what? So the standard model of particles, I won't talk much about this. Here they are. We know a lot about them. It's incredibly successful, except where it's not, as I said earlier. The neutrinos, we don't know a lot about the neutrinos, unlike almost every other particle here. We don't know the masses, for example. We don't really know how they interact. We can't put limits on some possible channels of interaction for them. Okay, and neutrinos come in 3 varieties. Flavors, which are the weak interaction states that determine how neutrinos interact in matter: electron flavor, muon flavor, and tau flavor. Of course, every particle here has an antiparticle, etc. Okay, so we like to measure the strengths of interactions in terms of a cross section, right? So you can think of a scattering experiment. There's a scattering rate on the left, there's a flux of particles, and then there's a cross section. So dimensionally, that works out okay. And just to set the scale here, the strong interaction is indeed strong. It goes like the cross-sectional area of the particle, and that can be very large because at low momentum, there's something like the de Broglie wavelength squared. Okay, so that could be quite large. The Thomson cross-section for photon-electron scattering. Okay, that's 10 to minus 24 square centimeters, 1 barn in nuclear physics language, like in the broadside of a barn. And the weak interaction, which is about 20 orders of magnitude weaker than electricity and magnetism, at least at the scales where we're interested in it in stars. And then there's gravitation, which is not even worth talking about. Okay. You can see that it's very, very weak indeed. So the weak nuclear force is absolutely key in stellar evolution. Much about this force remains mysterious. So it's the subject of a lot of frontier research in elementary particle physics and nuclear physics and astrophysics. Despite its well-deserved name, weak, this force is the origin of all of humanity's energy sources. This slide I put in there for Tom Murphy. If he's on here, eat this, Tom. Okay. Fossil fuels, solar, nuclear fission, nuclear fusion, all of this comes from the weak interaction. What do you mean comes from the weak interaction? A lot of it comes from sunlight. Okay. All right. Okay. So what do I mean it comes from sunlight? The key thing that happens in stars is this fundamental weak interaction. The sun is made of protons. There's some helium there, left over from the Big Bang. To fuse 2 protons together, to fuse 4 protons together into a helium nucleus, you have to change 2 of the protons to neutrons. The only way to do that is a weak interaction. Here's Hans Bethe. He figured this out, and you can see it. Unfortunately, the resolution is not very good, but there it is at the top. Okay. So the deuteron is a nuclear bound state of a neutron or a proton. It's, of course, the most weakly bound stable nucleus. And we have to make those deuterons in stars in order to access nuclear energy. Nuclear energy is not all it's cracked up to be. You know, the radiation doesn't bother me. You just don't get much energy out. If you burn protons into helium, you get about 1% of the rest mass of the nucleons out. If you burn heavier nuclei to even heavier nuclei, you get about 0.1% of the rest mass out. And that's in contrast to gravitation, where you get a fair fraction of the rest mass liberated, perhaps as neutrinos or other particles. Okay. All right. So here's a picture of it's the sun in X-rays, great. Here's the sun in neutrinos. We can detect those. This is the famous picture from Super Canda. Of course, I put the angular scales about the same. If you understand that the nuclear reactions are incredibly sensitive functions of temperature, this source should be a point at the center here. So the angular resolution is not very good. Koshiba, the famous Japanese neutrino physicist who got the Nobel Prize for this, was famously, when queried by the Japanese Science Foundation about why this picture wasn't round, he famously said, "If you give us more funding, we can make it round." Okay, so neutrinos are the murder weapons when it comes to massive stars. And I have to give this T.S. Eliot quote from East Coker. "Oh, dark, 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 they all go into the dark, the vacant interstellar spaces, the vacant into the vacant." Okay, so here's a picture of an HR diagram for the evolution of the progenitor of supernova 1987A. Wonderful. This is in a Scientific American article, which I highly recommend, actually, by Tom Weaver and Stan Woosley. And so this is roughly a 25 solar mass star. Unlike the sun, it will burn hydrogen for 10 billion years. This thing burns hydrogen for about 11 million years. Okay. And by and by it collapses. See what it does. To understand why it collapses, we have to talk a little bit about entropy. Entropy is Boltzmann's constant times the log of the number of states or arrangements of the matter, many body states in thermal equilibrium. And I know that's true because it's on Boltzmann's too. Okay. So the way to think about entropy in this context in stars is the way Hans Bethe thought about it. So high entropy is a very disordered state. So I could have 6 protons in blue and 6 neutrons in red, all running helter-skelter, and each of them has 3 translational degrees of freedom, right? So there are 36 degrees of freedom. A low entropy configuration of that same number of nucleons would look like this. I glom them all together in a carbon-12 nucleus. And then at temperatures below the excited states of the carbon-12 nucleus, then I only have 3 degrees of freedom. Okay. So here's what happens in that 25 solar mass star. It burns hydrogen in a main sequence. And that main sequence is effectively just like the sun. This thing is hotter than the sun. Sun has a central temperature of about a keV. This is 5 keV. Oh, it's a heavier star, so it's got to be hotter. Okay, yeah, all right. The density is lower than the density of the sun. The density of the sun is about 100 grams per cubic centimeter. It's 5 grams per cubic centimeter. The sun takes 10 billion years to burn up its hydrogen. We're halfway through that, by the way. But who's counting? This thing burns up the hydrogen in about 7 million years. It burns the hydrogen to helium. The star has to contract to get to a higher density because helium, if I fuse 2 helium nuclei together, I get beryllium-8, which is unstable. So we have to have 3 alpha particles come together at once in the triple alpha reaction. So you can see that the density goes way up to do that. And the temperature has to go up as well because the Coulomb barriers are higher. And so that takes about 500,000 years. And helium will burn to carbon and oxygen. Okay. And the star will burn out its helium, and then the central part will quasi-statically contract. When you contract, you heat up. And eventually it'll light carbon and oxygen. And there's some other things in there on the way, but you'll see something interesting. Of course, the temperature has to go up and the density has to go up. The temperature has to go up because the Coulomb barriers are higher for these nuclei with larger numbers of protons. But you'll see that the burning time just greatly accelerates from core carbon oxygen burning onwards. Carbon burning onwards. Okay. And by you keep going. You burn carbon and oxygen to silicon eventually. And that takes about 6 months to do that. And then silicon will burn to quote unquote iron. Actually, it doesn't burn to iron, it burns to chemical equilibrium. So statistical equilibrium, where all the nuclear reactions that build up heavier nuclei, the rates for those are large and fast compared to everything else, and they're equal to the rates that tear the nuclei down. So that everything is in equilibrium, and all we need to do is know the masses of the nuclei and the temperature and their partition functions, so we can get the abundances and solve that question. Okay. Once I get there, it collapses. Okay. So if you look at this, you might say, oh, gee, as it collapses, the temperature is almost 1,000,000 electron volts. That's 10 to the 10 Kelvin. You might be impressed by that number. Don't be. Because the electron Fermi energy is at least 10 times higher than, maybe 20 times higher. The density is higher. Okay. So the electrons at the top of the Fermi sea is just the Pauli principle. You're jamming these electrons together, and that forces them up into higher momentum states. And so it is favorable for the electrons to capture on the protons that are inside these big nuclei. That robs you of support pressure. But the thing I want you to see here is that, unlike what you've been told, massive stars are giant refrigerators. That's what they do. And the reason that the burning stages are short here, so much shorter after the onset of core carbon oxygen burning, is because the luminosity of the star is now dominated by neutrino emission. The star is furiously fusing stuff together, and all of that energy is pretty much getting dumped out in neutrinos that just escape. So the neutrinos are refrigerating the core. You might say, well, the temperature is high. Yeah, but it's thermodynamically very cold. Okay. So in fact, if you compare these big nuclei, if you compare the Coulomb energy between them, the electrostatic Coulomb energy between them to KT, the temperature, you'll see that Coulomb energy is sometimes larger, depending on the equation of state. So the collapsing core of a supernova can be a frozen Coulomb crystalline solid. That's cold. Okay. And so what happens, I'll put iron in quotes because this can happen, the collapse can happen even when the star is not gone all the way to iron. It can happen because of this Feynman-Enchanted cigar instability, even when you haven't even gotten as far, you're burning to oxygen and neon. So once it goes, this core is about the size of the Earth. It's effectively a white dwarf because it's supported by relativistically degenerate electrons moving near the speed of light. And so it's about Earth size, and it's got about the mass of the sun, about 40% more than the mass of the sun. In about 1 second, once it goes unstable, that thing will collapse down to a neutron star that if it first has a size about 1 second down to a size that's something like, I don't know, 30 kilometers, 40 kilometers, something like that. In another second, it's down to 10 kilometers, 6 miles. So think about that. That releases a lot of gravitational binding energy. Along the way, as it's collapsing, the entropy per baryon has gone from about 10 units of Boltzmann's constant when the star was burning hydrogen, down to about 1 unit of Boltzmann's. So if you think about the entropy per baryon of the the air molecules in the room here, it's sort of similar to what the entropy is when it's burning hydrogen, which is at first blush why you think entropy is an utterly useless quantity, right? But in fact, there's a big difference in order of matter between an entropy of 10 units of Boltzmann's constant per baryon and 1. Okay, these are big nuclei. The average nuclear mass number is about 100. These are nuclei that don't exist in the laboratory. We can't study them in the laboratory. Moreover, they're in very highly excited states. These heavy nuclei could be 30 MeV above ground. So these are very, very exotic things. And a lot of what we do in nuclear astrophysics and the weak interaction is trying to understand the weak interaction properties of these guys. So I'll give a shout out to Raul Herrera, who's a graduate student here a couple years ago, and Calvin Johnson, who are experts in this business. And so electrons capture on these, and by the weak interaction comes into equilibrium as well. So what happens in this collapse? The total optical and kinetic energy in a core collapse supernova that gives you the visual display on the sky, like the first slide I showed, about 10 to the 51 ergs. But the total amount of energy released in neutrinos in the collapse is 100 times that. And that's the explosion energy. That's only about 1% of the neutrino energy. And that energy is really the gravitational binding energy in this thing collapsing from something the size of the Earth down to something like the size of Greater La Jolla. Okay, and that's about 10% of the star's rest mass, and that gets dumped into the neutrino fields. Some of those are trapped in the collapsing core. Some of them get out. So you can think of that binding energy like this, and kind of the neutrinos diffuse inside this collapsing star until they get to a point where their effective optical depth becomes large and it becomes small, and they escape. We call that place the neutrino sphere, roughly the edge of this protoneutron star. But the figure of merit I want you to come away with from this slide is that the explosion energy is tiny compared to the gravitational binding energy and the energy that's in the neutrinos. Okay. And the name of the game for supernova modelers is to figure out how to get roughly 1% of the neutrino energy coupled into the shock wave that's formed when this collapsing core hits bottom, hits nuclear. When the nucleons start to touch one another, this collapsing core will just come to a dead halt, like hitting a brick wall. That launches a shock wave. The neutrinos by and by somehow re-energize it. Here's a slide from Tony Mason Kappa about how hydrodynamic and convective light motion can transport neutrino energy from the neutron star out to the base of the shock. This is a very difficult problem. Some people say, oh, it's so difficult, you guys could never figure out how supernovae work. That's not true. We always have an explanation for how supernovae work. It changes every 5 years. Okay. All right. Now, what about beyond standard model physics? I said that we might not have all the physics that we need here. After all, what I just showed you was a pretty exotic environment where the neutrino number density is gigantic. Okay. What about neutrinos themselves? In fact, there's a long history in particle physics of interesting things that neutrinos might do. And of course, the pioneer in this was Bruno Pontecorvo in the Soviet Union, who recognized that there could be kind of neutrinos that once neutrinos have mass, and we know they have mass, once they have mass, and there can be all kinds of interesting things that properties that neutrinos might have, including neutrinos that don't interact via the weak interaction, so-called sterile neutrinos. And this is old. This idea is quite old. So we can ask this question: is there a rich neutrino dark sector? Are there dark sectors in particle physics that have their own neutrinos or neutrino-like properties? As basically a neutrino here is a fermion, a spin-a-half fermion with no electric charge. Moreover, one can ask if these are a part of the dark matter, and so there's a whole sterile neutrino mafia here. at UCSD. This is kind of a UCSD thing. Chad is laughing, but he's actually part of that mafia. And so as Jake Spisak here and Lukas Graf. So we're having a good time trying to figure out whether sterile neutrinos could be the dark matter. And so far, X-ray astronomy seems to be our enemy. Okay. But there are hints from the experiments, from the accelerator-based experiments, that there might be dark sectors and there might be interesting physics in this regime. So here are experiments at Fermilab. Here's one possibility for the anomaly that's seen in LSMD, and maybe even seen in micromoon, a mini moon and micromoon. And so here's something with a dark Z and a dark neutrino, and that mass might be of order, say, hundreds of MeV. Okay, interesting. We could ask, what does that do in the collapsing core? And the answer is, it could transport energy. It could aid in the explosion. So here's a slide from Anna Saliga. Anna is an NTS postdoc, and I think she'll be here next year. And so the sterile neutrino, an active neutrino, might rattle around in the core, turn into a sterile neutrino that zips out because it doesn't have any interactions, turns back into an active neutrino. And the net result of that might be to effectively increase the transport rate of energy from deep in the core to the outside. And we can put constraints on that. Here are constraints on dark matter, for example. Also, what about neutrino-neutrino interactions themselves? Do we know for sure that neutrinos, I have one neutrino interacting only with another neutrino, not with a charged lepton? How do I know it doesn't have some new kind of interaction, a secret interaction that only the neutrinos know about? In fact, there are some particle physics possibilities. I wouldn't call it a motivation, but possibilities for these. I show this one. Here are heavy sterile neutrinos. I show this because Chad works on this and his students work on this. So Hannah Rasmussen, for example, is one of Chad's students at USD, wrote this very nice paper with Chad and a number of his other students. And this is an old game. We're still looking at this, whether or not heavy sterile neutrinos could screw up the early universe in some interesting way that we can either constrain or see the fingerprints of on Big Bang nuclear synthesis. Here are other members of the sterile neutrino mafia, by the way. We even count Graciela Gelmini, an otherwise legitimate particle physicist, has now joined our crime family. And Kev Abazajian at Irvine, many of you know him. He was my student also. And Alex Gusenko at UCLA is one of the chief theorists involved in this work. So you can ask about this. What about non-standard interactions, otherwise known as secret neutrino-neutrino interactions? So lots of work on this, including by Evan Rose, who was a student here, Mani Broda Sen, and Lukas Graf, and I and Evan are working on looking at what this might do in the early universe. And eventually we're going to look at what it does in collapse as well. And so you might have interactions given by some Lagrangian like that. For example, and these may be effectively flavor changing neutral currents, like change flavor. For example, then I could open up phase space that otherwise wouldn't be there. And so you can look at that, and so we do. And so one thing I showed you is that the entropy in the collapse in the standard model is quite low. Very low entropy. What would happen now if I have a degenerate sea of electrons, a degenerate sea of electron neutrinos? What if I start converting electron neutrinos via secret interactions into other flavors, mu or tau neutrinos? That opens holes in the electron neutrino distribution, and that allows some electron capture to go, or at least you'll readjust the Fermi levels of the electrons and the chemical potentials of the electrons and the neutrinos. And what that could do is generate entropy, heat. Now, if you generate something of order 3 units of Boltzmann's constant per baryon, you can melt all those nuclei, those giant nuclei I just talked about. That would change stuff. Now, instead of the core collapsing as, almost at the free fall rate until it hits nuclear density, now you'd start to, once the neutrinos start interacting with each other, you would generate entropy, and that would start melting nuclei, and the Maxwell-Boltzmann pressure would come up, and instead of the star coming in and bouncing, and hitting nuclear density, now it's just going to go, it's going to slow down as the pressure comes up. No shock wave. Okay, you might say, well, that doesn't happen because we know that supernovae explode. Well, but wait, remember the energy in the explosion is tiny. It's only 1% of the energy in the neutrinos. So there could be a lot of mischief in the neutrino sector, and we could still get an explosion. That's the disturbing thing here. It's an opportunity, but it's also kind of a barrier. Okay. So here are some calculations I did a long time ago with Jim Wilson and Lon Bailey. This is kind of the standard model, and you can see here, here's the electron fraction, the number of electrons per baryon, and that goes down as time goes on in milliseconds. Here's the bounce of the core. For example, here's the difference in the neutron and proton chemical potentials. And here's the mass fraction in heavy nuclei times 10. And you can see that it's almost all heavy nuclei until the nuclei all merge at nuclear density. But now we turn on a radical kind of neutrino-neutrino interaction, things change dramatically. Now what happens is that as soon as the neutrinos start to interact with one another, those interactions can be very fast, and the neutrinos can self-trap themselves and thermalize among themselves to a temperature T nu that's different from the matter temperature. And then those neutrinos only feel the matter through the ordinary weak interaction. So this is a complicated transport problem, and it's not clear what will happen. And we're working on that. And I think I failed to mention that, yes, these folks, Anna Saliga and Lukas and Kyle Herrer and Shashank Shalgar and Oliver Scholler were trying to work this out in a kind of more modern context. Now, I was bemoaning the fact the other day that we don't really have a neutrino collider. And of course, one of our experts at UCSD on this subject is Lukas Graf. He's sitting in the back, and he said, no, of course we have a neutrino collider. It's called neutrinoless double beta decay experiments, where two neutrinos can actually, with two neutrons change into two protons. We can look at that. And I'll just say here that we have a lot of experts on this here at this institution. Lukas, of course, in the theory part, and Liang Yang, who is an experimentalist who measures these things. Okay, now let me get to black hole mass gaps. So when this core collapses, it's going to make a neutron star. And if you know about neutron stars, you know that they are very close to gravitational instability. They're very relativistic beasts. Their metric deviations are something of order 10 or 20%. So they're already close to making a black hole. Sometimes for the bigger stars that collapse, they just collapse directly to a black hole. Okay. So this model we have seems to work pretty well. There are ranges of black hole masses that this model of stellar evolution can't really make a black hole in. These are the so-called mass gaps. So is there evidence for black holes with these awkward masses that are in the gaps that shouldn't be black hole masses? More murder? Are they murdered by dark matter or by more BSM physics? So let's look at this. So, of course, the advent of gravitational wave astronomy has been phenomenal. Here's one thing, GW 190521. This one has a subject of a lot of recent work as well. The best fit when I made this slide up was the merger of an 86 solar mass hole and a 65 solar mass hole fit with an in-spiral pattern. There's actually what's claimed to be a better fit that just has an unbound orbit, hyperbolic, just a kind of a head-on collision or nearly head-on collision, which is a bizarre thing if you think about it. It has to be in an environment where the black hole density is huge. And when you add these two things together, about 9 solar masses worth of the mass is radiated away as gravitational radiation. This is awkward. So if you look at the model of stellar evolution that we talked about, it's very hard to figure out how you get a black hole with a mass of 50 to 150 solar masses. But the cores of these things would make masses like that. Well, it doesn't make any sense. Our model tells us that they should explode for reasons I'll tell you about in a second. There's another mass gap. What if we find black holes with masses that are below that Chandrasekhar mass, the mass of that core that collapses? That would be awkward. In fact, in that model I discussed, it's really hard to figure out how you get a black hole with a mass less than about 2.5 solar masses. Okay. So is there evidence for those guys? Okay. So one way we might think of making a low mass black hole is to take a neutron star, otherwise manufactured in collapse like we just discussed, and now do something to it, to kill it, to turn it into a black hole. Okay. We would call that transmutations. That's a cool word that somebody made up. I think it might have been Tinnikov, I'm not sure. So let me switch gears for a second. The early universe is radiation dominated. And it was pointed out very early on that, of course, if it's radiation dominated and self-gravitating, it's very close to instability. And you could fairly easily get regions in the early universe collapsing into black holes. So are there black holes left over from the very early universe? This is an original idea by Zubovich from the mid-1960s. And now this field has exploded. There are a bazillion ways people can think of to manufacture black holes in the early universe. There's one problem. For the most part, they're all small. That may not be a problem. In fact, this is kind of an original idea for what dark matter might be. And so here's a this is from Marco Corelli. This is a kind of an old plot, but here's fraction of dark matter. Here is a primordial black hole, PDH rest mass, and you can see that there are lots of constraints on these guys being all of the dark matter. There's still actually a window open around 10 to the minus 11, 10 to the minus 14 to 10 to the minus 11 or 10, where they could be all the dark matter. There's actually kind of an event from microlensing from hypersupreme cam that looks like it could be, this is hypersupreme cam on the Super telescope that stares at the Andromeda galaxy. That's consistent with being a hole that's around 10 to the minus 10 solar masses, something like that. 10 minus 9 solar masses. So that could be there. Neutron stars are dense, nuclear matter density. So if these primordial black holes are part of the dark matter, you might think that in a region where the neutron star density is high, coincidentally where the dark matter density is high, like in the galactic center, that some of these neutrons, some of these black holes, primordial black holes, might get captured by the neutron star, essentially by body accretion. So here's a black hole in this mass range, and here's a neutron star. We kind of made it look kind of squashed. So this is the millisecond pulsar. Most neutron stars are millisecond pulsars. And the black hole gets captured. Okay, you can look and see what happens here. Effectively, it kind of settles down and gets captured. It takes about 10,000 years. Once it's captured, it kind of it consumes the neutron star from the inside out in about a day. It turns it into a black hole. So here's a simulation. Be very wary of simulations. They look pretty, but they always lie to you in some way. So, and this one is no exception. Okay? So I don't know if you saw that. Can you see the black hole? This is a neutron star. Millisecond pulsars are rotating effectively right near the breakup limit. So centrifugal forces are almost able to eject neutron-rich, very dense nuclear matter. So the idea here is that if you now dump something into it, like a primordial black hole, or certain other kinds of dark matter, you can actually eject some stuff. Let me show that again. You can see the black hole coming in from the left. This is a simulation by Diabatic. I'll tell you why it's a bit of a lie, which, David might be happy with showing this. Did you see the black hole come in? Mm-hmm. Now, as you see the black hole move around, see that? You see the wakes. These are shock waves in nuclear matter. They impart energy to the nuclear matter, and that could eject this nuclear matter. I'm not going to talk about the R process in this talk, but this is where we might get very neutron-rich and cold material ejected. And that might make interesting nucleosynthesis, make heavy nuclei like iodine and uranium and gold. Okay, now the problem is that Radice is a master at numerical relativity, but unfortunately, the only thing that the resolution of his code could handle at this time is not making a 10 to the minus 10 solar mass black hole, but 3% of a solar mass. So there's a difference in the effects. And so that's why I'm saying this is a bit of a misleading figure, but it's fun to look at anyway. Okay, so we might make those and we might transmute black holes, neutron stars, into low mass black holes. And that would be very interesting. So Volodymyr Feklistov is one of the leaders in trying to figure out the physics of transmuting white dwarfs and neutron stars by various kinds of dark matter and primordial black holes into black holes. And so he has an interesting test for how, if we build up lots of statistics with all the gravitational wave observatories in the future, we might be able to tell the difference between, we might be able to actually spot some of these guys and see whether or not we're making these, we really have low mass black holes. So in particular, there's this, these two guys, these two gravitational wave sources are consistent in the fits are not that great, with masses for black holes in the 1.5 to about 2.5 solar mass range. But again, the statistics are not real good. So don't really know for sure. All we can say is there's a lot of speculation that these guys were small holes. And did you make, if they are, did you make them by killing neutron stars, by transmuting them with dark matter? Or did they get made in the very early universe? Are they primordial holes? Or do we not understand something about stellar evolution? Now, I'm willing to bet that the latter might be the main explanation for this, but we can't rule this out yet. So maybe as we build up statistics in the future, we can get a handle on that. What about the high mass black holes, the high mass gap? Let me come back to that. So that would be a progenitor that would fall in this range, a order of hundreds of solar masses. Okay, so they're unlike the core collapse I just talked about, because those stars will burn hydrogen to helium stably. They'll burn helium to carbon and oxygen stably. When they quasi-statically contract and heat up and go to light carbon and oxygen, they'll suffer what we call the electron-positron pair instability. So the pressure average value of the adiabatic index will fall below 4/3, and those guys will go down. Why? Essentially, it's this. There's a range of masses where when you squeeze on it, remember what the adiabatic index is. Squeeze quickly. Look at the increase in pressure for an increase in density, but do it quickly so that no heat flows. So now when you squeeze it, what's going to happen is that some of your pressure was coming from electrons and positrons, okay, and photons. And when you squeeze it, you're just going to drive more photons to make electron-positron pairs. And those pairs right at threshold will not be moving at the speed of light. And so that gives you an adiabatic index, which is less than 4/3. That's the pair instability, and they'll go down. So once they start to collapse, you have to ask yourself this question. Now nuclear reactions are going like crazy, but what did I tell you? I said that burning heavier nuclei to even heavier nuclei, you don't get much energy out. You only get about 1/10% of the rest mass of the nucleon. So you don't have much nuclear energy to play with. So you're dumping in nuclear energy, but this thing is accelerating in its collapse, building up infall kinetic energy. And there's a question of how quickly you can add the nuclear energy. When you do those calculations in the numerical simulations, you'll find that there's a range of masses. This is the mass gap, where you'll get an explosion, where the nuclear energy generated is enough to turn this thing around and get it to expand before it gets too deep in the gravitational potential well. Okay. So if there really are black holes in those mass gaps, how do we get them? Interestingly, there are a bazillion ideas. There are all kinds of papers being written on this by the Fermilab group, by CERN group, many others. And there are two ways you can do it, which seem a little bit at odds with each other. You can add energy. You can add energy via dark matter particle annihilation. And that can work. That can get this thing to collapse and not add nuclear energy fast enough. Or you can add extra energy loss channels through emission of, for example, new light degrees of freedom, scalar particles or something like that. That would cause the star to consume fuel more rapidly because it's cooling faster. Remember what happens when you cool off, you heat up. So you emit more of these things. And the net result of this is that helium burning will end sooner. That means there's less oxygen-16 available to burn when the collapse occurs. And that will probably reduce your probability of getting explosion. So you can see that this is a wide open business. There's a lot of activity now in trying to figure out what's going on with these big stars. This interesting synergy between gravitational wave data and fitting, and from the laboratory, from the particle physics laboratory, and from modeling of stellar evolution. So I'll just leave it at that.
Questions for George?
Okay, so the way I understand it, like from beyond standard model, like general relativity ain't compatible with the standard model.
No, it's general relativity is fine. It stands apart from our models of particle physics. That may be an issue, but we know general relativity works.
But like if you try to unify it, doesn't that like isn't that like the failure of the equivalent?
I'm sorry, can't hear.
Sorry, so like if you're trying to unify them, that's like what I need to get to is like, so you're talking about like stable neutrinos and how that can like prove that would be a violation of the equivalent.
Yeah, that's beyond standard model physics, right?
So I'm still about like how you like that would prove a violation of the equivalent principle. I'm trying to.
It doesn't violate the equivalence principle at all.
Okay.
In fact, we're using the key properties of gravitation and general relativity to actually figure out what these new kinds of particles would do. Okay, it's just a new kind of particle that could be created from the standard model particles or from thermal processes that are happening in these stars. And remember, these environments are really exotic. This is something we can't really mock up in the laboratory very easily at all. But the environments in these stars are so exotic that they could manufacture these new particles that would be hard to find in laboratory experiments. I hope that helps. Sasha.
When I talk to like particle physicists, like Professor Ochoa at UCSD, for example, they're so against like the idea of sterile neutrinos. But
Who's against it?
never mind. But when I talk to like astrophysicists, they're much more for it. So would you be inclined to like give a general sketch of like
Oh, that's an interesting sociological question. So Chad and I can tell you about that over a beer sometime.
really?
It's an interesting sociological question.
What are like the frontiers of tech?
And I'll say that part of this breaks down in terms of nationality as well. American particle physicists were never terribly interested in the neutrino sector. That's not true of Europeans, especially Russians and Italians. Okay, we can talk about it.
Thank you.
So I was wondering, in terms of like
observational consequences that one might search for, so which stars can create black holes that exist in mass gaps or collapse to form black holes without an explosion or those sorts of things. Is there a nucleosynthesis signature?
Excellent question. So, I mean, what would be the nucleosynthesis from one of these parent stability supernovae, for example? If you know, it's going to look something like a type 1A supernova. That's something I didn't talk about at all. I don't really care about type 1A supernovae because they don't really make a lot of neutrinos. But those are thermonuclear explosions. So the energy to get that explosion is coming from nuclear reactions. Well, not a lot of energy. Ironically, they're much brighter than core collapse supernovae, like type 1A supernovae, for example. The answer to your question is we incinerate the material to nuclear statistical equilibrium. So they would make a lot of iron, a lot of nickel, a lot of cobalt. Whereas the core collapse supernovae don't make so much. Core collapse supernovae are going to make intermediate mass nuclei, silicon, magnesium, neon, and that will be ejected, lifted off when the shock wave passes out. So that one way I can answer your question, Karen, is that if we had a really good record of the chemical evolution, of the evolution of the abundances very early on, we might be able to ferret this out. So you'd be looking for something that didn't look right. A massive star that's going to end quickly, its life is short, and it's going to dump in stuff that looks like it comes from a type 1A. But you know the type 1A supernovae don't turn on right away. They only turn on very much later when we have evolved white dwarfs.
Well, I mean, something I was considering is like, if we can now, go to nearby galaxies and with IFUs map out all of the regions of massive star formation, and if there were a signature of like a ton of iron or something.
Yeah, something that would look anomalous that way. Now, do we even know that there are stars like this? I mean, there's the R136 region in 30 Diabatic. We had a talk on that a little while ago, and there are all kinds of ideas about how there could be like 500 solar mass objects there. The masses keep going down as the resolution gets better. That's a little suspicious, right? But there's still hundreds of solar masses. So we may even know that these things exist. Right?
Yeah, I mean, that's possible. It might be, I mean, the fact that you could maybe look at where those supernova happened and see an excess of iron for a much longer time than you might see them exist, for instance.
Yeah, it might look wrong. You might have expected mostly kind of typical core collapse supernova nucleosynthesis, so intermediate mass things, alpha elements, for example, and then there's some weird peak and peak up in the iron abundances. Yeah.
So we have one question from Anna online, and I think then we'll take that as the last question, and then we'll let the grads meet with you. So Anna, can you speak?
Yeah. Hi. Yeah, really nice talk. I had some questions about, because I've been looking a lot into these supermassive stars, mostly massive stars that can form under high accretion rates. So the protostellar evolution is really interesting. So the stars that you talk about that could reach 10 to the 4 solar masses, that's been studied for supermassive black hole seeds. And it turns out if you have high enough accretion rates, the stars themselves will actually just grow in radius as they grow in mass and tend to be relatively cool. And so basically, at least in the papers I've read that just studied the protostellar evolution, so just doing these 1D protostellar evolution models, hydrostatic models, they find that, if you have an accretion rate of 0.1 to 1 solar masses per year, you can get stars, you should be able to get stars that big. However, you're basically a protostar the whole time. And then once you reach 10 to the 4 solar masses or above, then you become GR unstable and collapse. So if I'll send you an email. We should chat more about this because I'm looking at lower mass accretion rates in the context of trying to make massive stars like greater than 200, 300 solar masses. But anyways, so they basically say you get a direct class black hole, but I know there hasn't been so much work on that because it's a protostar. It hasn't undergone any hydrogen fusion and this and that. Yeah. Any idea of what a black hole from that would look like?
Well, yeah, I mean, it should be a very massive black hole.
Yeah, that's why,
And
that's
so
why.
I would
it's
I would
great.
imagine if you're doing this in an environment where you're forming stars, there's a lot of gas around as well. And so you might
Yeah.
look for accretion on, that didn't look quite right, on what we would call an intermediate mass black hole, right? Something that's got a mass of order hundreds of solar masses.
Well, so this is mostly evoked for early universe, so like first star, pop 3 stars formation, where you basically have halo collapse, and that can lead you to these really high accretion rates. So typically like galactic accretion rates for massive star formations like 10 to the -3, 10 to the -4 solar masses per year. But once you go above 10 to the -3 solar masses per year, the protostellar evolution gets very interesting in the sense that you can, you don't contract as easily to the main sequence. You can actually, like, depending on the accretion rate, have multiple phases of being bloated. And that's what really lets you be able to get to higher masses. For these, you expect at the very early universe, for the first stars, for the halo collapse, that you could potentially achieve accretion rates that high. So it's only really invoked for pop 3 star formation, and in the case of being these supermassive black hole seeds. I'm looking at like a bit lower, like a few times 10 to the -3 to like 10 to the -2, in the context of massive, like more massive stars, but several hundred to 1,000 solar masses, because then feedback becomes way less important, and then you can keep accreting.
I love it.
Yeah.
So I want you to think about, it'd be fun to talk about this, Anna. And one slide I didn't show here was this idea about compact dark objects. If there are dark sectors, we have a visitor here in the particle theory group, Daniel Stolowski, who my group is talking with, who gives a very nice, has a paper with a nice example of hidden sectors, dark sectors. And there you might have dissipation in these dark sector particles, and you might form gravitational potential wells in that way that then accrete baryons. So
Okay.
we might be wanting to corrupt you into using your calculations to look at some illegitimate stuff like this.
Okay, I'll send you an email. We can chat more, and I'll send you some papers. It's mostly work by Hosokawa that's been looked into this, but it's really interesting.
Very good, Anna.
Thank you.
Thank you, everyone online and here, and give George a round of applause.